formate. So now we're going to introduce how the solar system came to be the solar system we have. The things we're going to include in this model, we're going to remind you of energy is conserved. Energy is conserved in a closed system. This will be an important thing to understand. We're going to talk a little bit about how forces mediate the transition of energy. Hey, welcome aboard. Yeah. We're going to talk about how forces mediate the transition of energy. So what you're going to see here is there'll generally be a stage of formation. You'll see up at the top, we'll have a stage of formation. I will probably include a little bit of graphics. Hopefully I'll also include proper spelling. Then I'm going to talk about what's happening in sort of a grand physical system. System on the left end of things here. And during the stage of formation, I'll also include some terms because one of the challenges again with this in pretty much any science class is the amount of new words. P-H-Y-S-I-C. There we go. Yeah. Physical system. So the first stage of forming our solar system involves a supernova. You can sort of think of this as a collapse of a very large star. Put that in parentheses. So here we go. So supernova, these are stars about 10 times as large as the sun. And when they collapse, what happens is you get nuclear, what you're seeing is nuclear reactions, atomic energy. Atomic energy is going to be converted into kinetic energy. Atomic energy, and what mediates this transition is, and what's mediating this transition, I'm going to see if I can use a smaller font here. There we go, 18-point font right here. And what mediates this transition is the nuclear forces and converting it and electromagnetic forces. And what this is going to look like graphically, these are perhaps one of the most spectacular events that are commonly seen with the naked eye. Though I did get to watch the comet. That was pretty amazing. That Neowise comet, that was pretty awesome. But this is one of those things like, I hope I live to see a supernova explosion in our galaxy in our lifetime, which for a while, we thought the star Betelgeuse was going to go supernova. And I was like, yes, 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 yes. Didn't happen, but it's a star with a fairly large star. And the star basically collapses in on itself. You get a bunch of very violent, rapid nuclear reactions, and that starts sending matter flying everywhere. Put a little labeling here. Matter going. Put some more colors on here. There we go. Matter flies every which direction. It is truly a spectacular event. If one of these were to happen in our galaxy, we would be able to see it. First of all, the sight would last for days to weeks, and we would be able to see it during the daytime. It would look even brighter during the nighttime, but that would be... And in human history, there's been a couple of these recorded where suddenly a very large, very bright star appeared out of nowhere. And we've definitely seen them in other galaxies with the telescopes we have now. So stage two here is eventually all that atomic energy, all that matter is going to, as it flies further and further away, it stills matter. And the thing about the gravitational force is that as long as there's a gravitational force present, matter is going to attract matter. So as that matter is flying away, it starts to slow down. And again, as it slows down, all that widely scattered gas and dust is what gives you your nebula. So what you're starting to see here in your physical system is gravity. Gravity Gravity is going to convert kinetic energy into potential energy. And this nebula is kind of like this sort of slow stopping point. So this is where you're seeing all those really cool sort of psychedelic colors. But again, this nebula is being held together. Let's get some black stuff in here. Fun. Yeah. But all this gravity, all this matter is still gravitationally attracted to itself. And so, for example, what you see in this Horsehead Nebula is you start to notice right here along the edge, what appears to be the edges of this is actually the pillars of creation, some very bright spots where it looks like a lot of that matter is starting to come together. This is gravity again. Gravity starts to draw the matter inward. As the matter starts to fly inward, it's going to sort of, most of that matter is going to coalesce near the center of everything. You'll end up with a very faint, large, faint protosun. Matter starts flying inward, and most of it flies in and forms your sort of early protosun. Matter drawn inward by gravity. Solid matter is widely scattered, starts to be drawn inward by gravity because all that matter is attracting to other things. Now, most of this matter will form a sun, but some of that matter, as it's flying in, flies in so rapidly that it actually overshoots matter. And I think for our solar system, that's about 2% of the matter ended up in orbit around the sun, whereas most of the matter during the accretion event ended up basically forming the sun. Now, here's what's also starting to happen during accretion. So what you're seeing energetically, physically here, is you're seeing gravity is now converting your potential energy back to kinetic energy. But then what's also happening is you're starting to see a lot of collisions. And so the second video you're going to see posted this week is going to be a video of a demo where I kind of show, using a piece of spandex, a hula hoop, and other objects, how the solar system comes together and what happens when a piece of matter is flying fast enough that it kind of overshoots the sun and starts going in orbit, and why it is we also don't have a lot of matter, why most objects orbiting the sun orbit one direction rather than the other. So what starts to happen is collisions. Your collisions will start to heat things up. Start to heat things up. Now, as you start getting collisions, you start to get a proto-solar system. Stage 4 proto-solar system. So you still have a fairly faint sun. The sun stays still a really faint, whoops, wrong button. Still have a faint sun at the center of your solar system, but now it's going to be surrounded by lots and lots of orbiting bodies. Lots of them. They're going to be the orbits are going to be irregular. They're going to be different shapes. Those orbits are going to be crossing each other quite a bit, and so you're going to see lots and lots of collisions in the very early solar system. Increasing collisions. So you see lots of objects in very nearby orbits colliding with one another. Right. Orbits favors buildup of larger objects. Larger objects are going to start to be favored by this process. Finally, what starts to happen is these larger objects have a stronger gravitational pull. So in addition to all these objects colliding, you also have lots of gas and dust around here. Let's use a bigger pen. So it starts to happen as some of these larger objects start to stabilize. And so what starts to happen is the larger objects, not only sort of surviving collisions, they're also drawing in gas and dust that are near their orbital path. And so we start to see by the end of, later on, this happened about 4.6 billion years ago in our solar system, you see a stable, we're going to put stable in quotation marks, a stable solar system. And dust. And by this point, what's happening is that objects are far enough away from each other gravitationally. Let's see if we can get this. And the smaller objects are obliterated generally, or they find some place where they're not colliding with anything. So for example, our asteroid belts are a great example of this. And this is how we get our sort of final solar system. So I'm going to save this. I'm going to post it up in discussion.